Hi everybody, this is Gigi from Kauai Community College. In this video, we will be talking about regions between curves. Alright, so let's get started. Now suppose you have an area in between the function f of x, which is the blue one, and the function g of x, which is the red one, right? That's an odd looking shape. So what we have learned probably from previous lessons were that we could go ahead and divide this area up into really small rectangles like these, yeah? And then what we're gonna do is we're gonna find the area of these small little rectangles here, and then we're gonna add them up, right? And that would be the area of the bigger shape, right? Now, so what I'm gonna do is I'm gonna go ahead and blow up that rectangle, one of those rectangles that is in here, so we can have a larger picture to take a look at. No, do not want the circle, want a rectangle. Okay. So like suppose this is the rectangle that we're talking about right here, okay? Suppose that's our rectangle. I blew it up just a little bit so we can see, right? So let's say that's our rectangle right there. And so what we're gonna think about this is what is the height and what is the base of that rectangle, okay? So the height of the rectangle is this part right here, right? So this part right here is the height of the rectangle, and then this part right here is the base of the rectangle, right? So what we're doing is we're dividing up this rectangle, the shape that go from A to B, right? Let's go from A to B, and we are dividing it up into like maybe n number of rectangles, okay? So we can see that the base at the beginning, we would say, okay, well, let's take the length b minus a, and then that is coming from A to B, and then we are going to divide it up into n rectangles, so divided by n, and that would be how long that base is, right? Now we can then define this to be what we have seen before, delta x. Okay, so that right there is delta x. Okay, and then so this right here is delta x. That's the base, right? And then the height of the rectangle, is the difference between the two functions. So it would be the blue minus the red, so that would be f of x sub k, meaning like that this particular f of x sub k right there, minus this particular g of x sub k right there. Okay, that is the height of the rectangle. Okay, now then what are we gonna do? Then the area of one rectangle is base times height, right? So we would say it would be f of x sub k minus g of x sub k, that base times the height, delta x. Okay, now we are though going to go ahead and add up a bunch of rectangles, right? There are n rectangles in there. So we were gonna say that the area of that shape the area, the total area of that shape is going to be, and you've seen this before, the sum, okay, that goes from 1 to n of all of these area, all of these rectangles. So f of x sub k minus g of x sub k multiplied by delta x. Okay, now really, how many rectangles do you have to cut so that you can get a very accurate amount that represent the area of that, right? So we know that the bigger n is, meaning the more rectangles you cut up, the better approximation we'll get to the exact area of that rectangle, right? So, and you have probably seen this before. What happened when we say let n be bigger and bigger and bigger, right? So you get it. Now we would say the limit as n goes to infinity, right, of this sum right here, k equal 1 to n, and that right there is what we call the Riemann sum of the area minus g of x sub k all multiplied by delta x. Now that is the definition of what we say an integral, right? That is an integral. That is an integral right there. When you take the limit of the Riemann sum, you have an integral. And you have seen that before, and that integral is the integral from, okay, the integral from a to b, okay, of f of x minus g of x, and then we would say we are taking the integral with respect to x. That is the dx. Okay, and that is the area of that shape where you have a vertical strip. The base of the strip, in this case, we can think of it as delta x, or we say in this case dx when we are talking integral, right? And the height of that strip would be the function f of x minus g of x. So we would say take the integral from a to b. That means we're going to sum it off from all the way to a, from a to b, of the area of each rectangle. And that is how. All right, now here, what's the difference between this picture and the previous one we had? Well, it looks like your graphs are going sideways, right? So first of all, you can see how the function is being written. It's x. X is being written in terms of y, so that is why your graph goes sideways, right? Now, if it's like that, then when we are visualizing our rectangular strips, we are seeing horizontal strips like this, right? Okay, again, what I'm going to do is I am going to blow up one of those rectangles so that we can see a little bit better. Okay, so here is that rectangle I'm going to blow up right there. Okay, we would now still the same thing. Think about the base and the height of that rectangle. Okay, so in this case though, because this goes horizontal, we would say my base goes from, is part of the segment C to D, right? So it would be the base of that rectangle is d minus c divided by how many rectangles do we have? Well, let's say we have n of them. Okay, and then again, we are going to define that as delta y in this case, change in y. Okay, so that's that is the base of the rectangle. So right here, this right here is delta y, that one, the base of that rectangle, right? And then the height of the rectangle is kind of weird to call this the height when it's not standing straight up, but that what I meant by that is this part right here, going from here to there, right? So that is the height of that rectangle, is the difference. That's the distance between the two functions. So that would be the difference, and that would be f of y minus g of y, right? So then the area of one rectangle is, we would say, f of y minus g of y multiplied by the base, and that is delta y, right? Again, what are we going to do with all of these tiny, skinny rectangles? We are going to say, in order to find the total area, we are going to sum them up from 1 to, not infinity, but from 1 to n, because we have n rectangles, right? And then notation wise, what I'm gonna say is that I am going to say this is some particular k, right? Meaning that particular k rectangle right there. And I am gonna say now k would be from one rectangle to n rectangle, right? Rectangle number 1 to all the way to nth rectangle. And what I'm gonna do is go ahead and add up the sum of all of those area. And that would be base times height, and that is how that goes, right? Now, how are we gonna get a really good estimate? Again, the good estimate would be for n to be really big, so that our rectangular strips are very skinny, so that we can get a very good estimate, right? Good enough to say, oh, hey, that really is the area of that funny looking shape. So that really means for you to say, take the limit as n goes to infinity. That means let n be really large, so that our rectangular strips will be really skinny rectangular strips, and we have many of them. Okay, so what does that define? The limit of a Riemann sum defined on, again, integral, right? So in this case, it would be the integral from c to d, and that would be f of y minus g of y multiplied by, or take the integral with respect to, dy. Okay, so here we are thinking, because these are horizontal strips, the base of this horizontal strip is delta y, or you can think of it as dy, and the height of the rectangular strip would be the difference in the function values, and that is written in terms of y, because it is a horizontal strip. Okay, so that is how that works when you have horizontal rectangles.